Ladies and gentlemen, welcome. My name is Zdeněk Hanzálek, and this is the 69th talk of the scheduling seminar. First of all, let me ask Michael Pinedo to introduce the speaker.
Okay, our speaker today is Danny Hermelin. He is a professor of computer science at Gurion University in Beersheba in Israel. And originally he had made major contributions in graph theory. Then he turned to scaling, and he has already made major contribution in scaling. So if he is one of the experts, the world experts in fixed parameter tractability in scaling, and now he started working also on multi-objective scaling. He has some major results. And now he started working on fairness in repetitive scaling. I was just told by some people here, in the United States, we have congested airports. And one of the major problems in congested airport is the fairness in repetitive scaling. What slots are you given to which slots are you going to give to which airlines? And that's apparently a very, very, very big deal. So this is the topic that Danny is going to talk about today, so that you know a little bit about fairness. Okay, Danny, please go ahead.
Thank you. Thank you for the wonderful introduction, Mike. Thank you, Zdeněk, for the invitation. So yes, this is a talk about fairness in repetitive scheduling. That's the title of the talk. The talk is based actually on a few papers with a lot of authors. Among them, Mike Pinedo, who's with us here. On all of them, Dvir Shabtay, who's also in the seminar, is part of it. That's why he's on board. And the other co-authors are Klaus Heeger, Yuval Yitzhaki, George Merzios, Hendrik Molter, Rolf Niedermeier, and Danny Segev. Okay, so let me start by what a typical classical single-day scheduling problem looks like. Okay, so just a very basic thing that we first learn about scheduling. So most of these problems look like this. We have a set of n jobs. We can think of them as jobs, or let's say clients. And each job may have various characteristics. So each job always has a processing time. So the amount of time it requires, the processing time it requires. A weight, which could equal 1, which indicates its importance. Due date, which indicates when it's due. And this it sometimes has this, sometimes not. And it can also have a release date and several other characteristics as well. So a job basically is a set of numbers that define these various characteristics. Okay, so and typically in this case, let's assume that there's no release dates, release times. Schedule is simply just a permutation. When we have a single machine, it's just a permutation of the jobs. Okay, so if we have 3 jobs, we have 6 possible schedules, and this is the solution space of our problem. And in such a schedule, the completion time of any client or any job is simply the amount of processing time of all jobs before him, including the job J itself. Okay, so a complicated way to say this is the sum of over PIs over all I, which is not after J in the schedule. All jobs I which are not after J in the schedule. Okay, so this is the classical setting, and then each client or the clients may be interested in various things. They might want to minimize the completion time. So what we just discussed, the sum of processing times the time they complete their job. They might want to minimize their lateness, which is defined as the completion time minus their due date, assuming they have a due date. So how late the job completes with respect to their due date. Or they just might care about whether they're tardy or not. So if their job is before their due date, they're happy, 0. Otherwise, they're unhappy, 1. And there are, again, various other objectives. But this is generally how you describe a simple single machine scheduling problem. Now, a scheduler, basically, since we're the service providers, we can decide actually the objective of the schedule. And in certain situations, in actually a lot of situations, Mike was discussing one of them, we're very much interested in fairness. In some cases, maybe as much as profit or anything else, or sometimes even more, when we're a non-profit organization. So we might try to find a schedule which is fair, which we consider fair as much as possible to our clients. In the single day setting, in the single machine setting, one possible way to do this is just to minimize the total completion time of the schedule. So the sum of completion times of all clients. And this is basically equivalent to minimizing the average completion time of any client. So in this sense, it is somehow fair to our clients. Now, if we do want to minimize the total completion time, it is well known that we can use the shortest processing time rule, the SPT rule, where we sort the jobs from smallest processing time onwards. And this gives an optimal schedule. Okay, so in this case, we can find if we consider this fair enough. We can find in this setting a fair schedule quite easy. If the clients don't care necessarily about the completion time, they just don't want to be late. Well, we can minimize the total number of non-tardy jobs, or minimize, sorry, the number of tardy jobs, so sigma uj. And we can do this just by sorting the jobs according to their due dates, and then scanning the EDD order from left to right. And when we encounter a job which is tardy, we replace it with the largest job in the set of jobs that we already processed. So this is known as the Hodson-Moore algorithm, and in this case, we also have a very efficient algorithm for this objective function. But here, this is not clear at all if this is even fair, right? So if the clients just don't care, they just don't want to be late, it's not even clear that we have a good objective function in terms of fairness. But at least we can minimize the number of tardy jobs very efficiently. Okay, so this is the single day case. Now, what happens in the case where the clients keep returning? Right, we're a service provider, maybe a huge service provider. A lot of these service providers typically have the same clients coming over again. If you think about, I don't know, cloud providers, airports, etc., all of these service providers have the same clients, and these clients periodically demand service. So in the simplest case, all our clients keep on returning. They return each day of the month. And let's say we have, or whatever period, and let's say we have m days in the period. So in each client has m jobs, one per each m day of the period or month. And now we use the natural way to denote the characteristic of these jobs is to use this double subscript. So I will always denote the day in the stock, and J will always denote the client. And PIJ is the processing time of client J's job on the AI. Similarly, CIJ would be the completion time of client J's job on the AI. And we can also define WIJ, DIJ, and RIJ when necessary. In the stock, we won't need them. Okay, so each client keeps on returning each day. And each day they have a job. It could be the same job with the same characteristics. It could be a different job. Now, if we do what we did just for a single day, let's say we just try to minimize the completion time of all jobs, it could be the case that one client is completes last on every day. Okay, suppose one client always has the largest job. He will always complete last on every day. And you could say, okay, well, he has the largest job, maybe that's somehow fair. But if you think about this, this is particularly unfair when the processing time is not necessarily determined by the clients. So, for instance, in healthcare and civil duties and several other cases, the processing time of the service we demand is not exactly up to us. So in this case, it's really unfair if, and it could lead to a situation where a single client really gets the worst service overall in each day. If we, on the other hand, minimize the number of tardy jobs over all the period of all M days, again, it could mean that a single client would never get any service. His or her job would always be tardy. And from his perspective, it means that the job is just meaningless, let's say. And again, this is particularly unfair when the due dates are not exactly determined by the clients. It's also unfair, maybe unfair otherwise, but for sure it's unfair when the due dates are not exactly up to the clients. Okay, so the standard objective functions don't seem to be very good in the case of repetitive scheduling, the case of where the clients come repeatedly with a set of jobs every day. In this case, it makes much more sense to minimize, if we're interested in completion time, to minimize the maximum total completion time of any client over all M days. So we look at each client, J, and we sum up its completion time over all days. Let's call that CJ. And now we want to minimize the total completion time. We want to minimize all the CJs. So we want the client who has the largest completion time over all M days to have this completion time as small as possible. If we're just interested in tardiness or not, we can minimize the maximum total number of tardy jobs of each client over all M days. So you can think about it, if we're just trying to minimize the number of days that a client would not get any service, any client will not get any service, assuming that being tardy is not getting any service. And we can do this also for any objective function. So typically, in this talk, I just gave two examples of very classical objective functions, but you can think of any objective function Fij. Maybe it depends on the completion time of the CIJ, the completion time Cij. And now we define the fairness and repetitive scheduling problem, which we denote as follows. So one means single machine, repetitive in the second field means it's repetitive, and this is the objective function we're trying to minimize, which is the maximum, we're trying to minimize the maximum fj, where fj is the sum of fij of client j. Okay, so this is the problem we're dealing with. In the decision version of this problem, we're giving another parameter k. Let's say we call it the threshold, the fairness threshold, and we just want to determine whether there exists a schedule whose objective is at most k, where the maximum fj is at most k. Okay, so this is the model we propose to optimize fairness in repetitive scheduling in the most simplest form of repetitive scheduling. One way to think of this as we have, let's say, a performance matrix for which specifies the performance of each job on each day. So the rows are the days, the columns are the clients, and this is the performance of the second client's job on the second day. And the sum of the columns of the total objective of each client. Right, so the rows correspond to the days, the sum of the columns correspond to the total objective of the client. And what we want to do is we just want to minimize this final row, the maximum value in this final row. Okay. So this is the problem, the model we propose in general. And of course, you can plug in any objective function you want and you would get a different problem. And so the model is quite robust. You can easily add all your favorite machine models to it. So for instance, you can think of PQ, whatever objective function, and then you have on each day Q machines. You can also use different thresholds for each client. This is slightly, at first glance, doesn't seem so fair, but there are cases where there are different classes of clients, premium customers, etc., etc. So our model allows this. And it also allows various interesting variants that you can study. For instance, if you want to study the problem where you find a solution which is k fair for all but S clients, so for almost all clients, except for a very small group, you can easily study this problem using our model. Another interesting question is the price of fairness, the ratio between the global optimum and the best K fair solution. We have some very few results on this, but this is definitely another interesting question you can study on our model. So our model is very, in our opinion, or in my opinion at least, very robust. It can handle various variants, any kind of objective function you can think of, any machine model you can think of, almost, and various different questions. And today, what I want to present, I want to mostly focus on the total completion time objective. And if there's time at the end, I'll just briefly mention a few results that we have for other objective functions. Okay, so now we're talking about the single machine repetitive scheduling problem, where we want to minimize the maximum completion time, total completion time of any client over all n days. Okay, so we have initially some initial results, or not initial results. The first thing we considered is when the number of clients is relatively small. What happens if the number of clients is relatively small, but there are a lot of days? Can we do something there? And actually not. The problem is already weekly NP hard even for 2 clients, so for 2 more clients. But it is only weekly NP hard for 2 more clients. There is a pseudo polynomial time algorithm for a constant number of clients. So for when the number of clients is small, basically you also need that the processing times would be small, otherwise you can't do anything. And if they are small, it's solvable in polynomial time. So the number of clients case was basically the first case we solved. Then we thought about the fairness threshold K. What happens if the K is constant as well? And it turns out that this doesn't help too much also. The problem is already NP hard, this time strongly NP hard, even for K equals 37. And this also means this would be important for later on, that the problem is APXR, meaning it doesn't admit a Peters, most likely. So when you think about the number of clients or the fairness threshold, these don't help too much. But then we turn to consider the number of days. And here we show again that the problem is hard already when there are 4 or more days. But at least the problem is easy when there is 2 days. And this is a result that I want to present to you in this talk. But both of these results leave kind of an obvious gap, which is the first open problem that I want to present in the talk. And it's what happens, what is the complexity of the repetitive scheduling problem with total completion time objective on 3 days. We don't know if it's NP hard or if it's polynomial time solvable. And this is why. But for 2 days, we know the answer. It is polynomial time solvable. And this is what I want to present next. Okay, so suppose we want to minimize the total completion time of each client. And we have only 2 days. The clients repeat, come 2 days. Notice that if we have only 1 day, the problem is trivial. It's always trivial. Any repetitive scheduling problem almost is trivial. But for 2 days, it already gets interesting. So our algorithm is inspired by Johnson's algorithm for the 2-stage flow chart, minimizing make span on 2-stage flow chart setting. For those who know it will remind them. For those who don't, hopefully I can explain our algorithm without it. And the algorithm is based on a few properties that we discover for optimal schedules. And the first is the following property. So there's always an optimal schedule where the order on the first day and the second day are reversed. So the order of the second day is exactly the reverse order of the first day. Okay, so if we order Bob, Alice, and Charlie on the first day, then it's Charlie, Alice, and Bob on the second day. So this essentially means that it's enough just to determine the order on the first day. Once we have this, we know how an optimal solution would look like. Okay, why is this true? This follows by a simple swapping argument. So suppose that on both days we have two clients that violate this property. Let's say on both days Alice's job is before Bob's job. Okay, but they can complete whatever on each day. So we can do the following swap. We can take only on the first day Alice's job and put it, make it complete when Bob's job completed previously, and move Bob's job one step back. So basically this schedule. All right, so the order among other jobs doesn't change. We just move Alice all the way to you. So if you notice all other jobs, these jobs, the completion time gets decreased. These don't change. These don't change. So on the first day, the other guys only improve. Other clients' completion time can only improve or not change. However, if you think about it, notice that Alice's total completion time and Bob's total completion time, new completion time in our new solution is still less than the total completion time of Bob in the old solution. So therefore, we can definitely not increase the fairness threshold with such a swap. And if we repeat doing this for all violating pairs, eventually we get a schedule that satisfies this property, where the second day's order is exactly the first day order reversed. Okay, so now we know that there's an optimal solution that satisfies property one. And we will use this to find an actual optimal solution. For this, we will partition the clients to two types. So the first type of clients are the ones whose processing time on the first day is at most the processing time on the second day. Okay, so you can think about it. In the first day, they do slightly less or not as much as they do as the second day. And the second type is the clients with the opposite, the clients whose processing time on the first day is larger than the processing time on the second day. Okay, so they do more on the first day. And the solution the schedule we construct is we schedule first the jobs of type 1 in SPT order, so shortest processing time, an increasing order of shortest of processing times. And after that, we schedule type 2 jobs in LPT order, in decreasing order of processing times. Okay, from largest to smallest processing time. And then on day 2, we just do the reverse of day 1. Okay, and the claim is that this schedule is optimal. So how do we do this? We first consider only schedules which satisfy the first property. So optimal schedules where the second day is exactly the reverse of the first day. And now, excuse me. And now we show that the set of optimal solutions where property 1 holds includes a schedule where the following property holds, where always on the first day, type 1 clients are scheduled before type 2 clients. Okay, we call this property 2. How do we show this? Again, by a swapping argument. If we have an optimal schedule satisfying property 1 that doesn't satisfy property 2, then there's a violating pair which are scheduled adjacent to one another on both days, because day 2 is the reverse of day 1. And then we simply swap between the two of them, okay, to obtain a solution that looks like this. This swap changes nothing for the other clients, and it cannot increase the total completion time of both Alice and Bob. This is because Alice was of type 2 and Bob is of type 1. Alice does more on day 2. So Alice does more on day 1. Therefore, this swap improves the total completion time on day 1. So now we know that there's an optimal solution that satisfies property 1 and property 2. We now show that if there's such a solution, there's also include solution where the type 1 jobs are scheduled in SPT order and on day 1, and the type 2 clients are scheduled in NPT order on day 1 after order. Yeah, and actually it has to look like this. It has to look like this again. Why? Because of the swapping argument. If Charlie's job is larger than smaller than Alice's job, then a swap again changes nothing for the remaining clients, and the new total completion time, we can show that the new total completion time after the swap is at most Alice's old completion time. Okay, so this also doesn't hurt the fairness threshold, and once we have this, we show that there's an optimal solution that fulfills property 1, 2, and 3, and that's exactly the schedule that we constructed. So this is this algorithm runs in nearly linear time, is very quick, and on each day it somehow looks like Johnson's algorithm, for those who know. Great. Okay, so that's the 2 days algorithm. We can also show various other results. In particular, we consider the parameterized complexity of the problem. And we show that the problem is what is called strongly W1 hard when we parameterize by the number of days. What this means is it means that the problem is unlikely to admit an algorithm with this running time. So some function of n times the polynomial in n, where the degree of the polynomial doesn't depend on n. Unless unexpected things happen in complexity field. So there's no algorithm like this, even if the processing times are small. Even if the processing times are given in unary. But there is still an algorithm, there is still a possibility of an algorithm with running time n to some function of n when the processing times are small. And we do not know if such an algorithm exists. So for constant number of days, and there could be a pseudo polynomial time algorithm, essentially. And finally, as the last result that I'll mention, but not show, is we can show also that the problem, if we don't just use parameter n, but also k plus n, the problem now can be solved in f of k plus n times some polynomial in n. So if also the threshold, the fairness threshold is relatively small, you could do something slightly more efficient. But if this algorithm involves n-fold ILPs, which in general, this function is not so small. Not so big, but not so small. Okay, so this is basically what you can do if you think about, or what we know about the problem. If we're looking for an exact solution, if we want an exact fairness threshold, the best fairness threshold K. And the most, I guess, the most important problem here is what happens in 3 days. That's completely open. So moving on, what we considered what happens when you try to approximate the threshold, the fairness threshold. So suppose the optimal solution threshold is opt in our instance. We're interested in alpha approximate solutions or algorithms that produce alpha approximate solutions. And what is an alpha approximate solution? It has a fairness threshold K, where K is at most alpha times opt. Okay, so a 2 approximate solution produces a solution where the fairness threshold is at most twice the optimal fairness threshold. Okay, and we show, in this setting, we show various results. One result that I want to present to you is that the problem admits to approximation algorithm. So an algorithm that produces a solution whose fairness threshold is at most twice the optimum in polynomial time. So the algorithm runs in polynomial time, officially, formally, but behind the scenes, the algorithm solves many times, or uses many times an LP solver, which even using once might be too expensive with respect to time complexity. So already here I can state the second major open problem of the talk, or the second open problem of the talk. And it is, can you find a simple combinatorial, efficient combinatorial algorithm that achieves a constant approximation algorithm for this problem? Okay, so even an algorithm that only uses an LP solver once would be interesting, but even better, an algorithm that doesn't rely on linear programming somehow would be very interesting, and even if it achieves a worse constant than 2. Okay, so let me present the 2 approximation algorithm. The algorithm is inspired by the 3 approximation algorithm for the problem of minimizing the total weighted completion time on a single machine when jobs have release times. Due to Hall, Schultz, Schmoyes, and Vine from Mathabo 97. And it relies basically on the following LP. Okay, so here is a linear program, which in the slides would be denoted LP. First, let's discuss the variables. There are 2 types of variables. There is this capital K, which is the fairness threshold that we're trying to minimize. So that's our objective, to minimize K. And then there are the XIJs, which are just the completion time of the client's job. So XIJ equals the completion time of client J's job on the I. So these are the variables. The linear program has 2 types of constraints, 2 sets of constraints. The first set is very natural, right? We want to make sure, since K is our fairness threshold, we want to guarantee that the total completion time of any client is at most K, and that's what the first constraint say. You sum up over all n days the completion time of client J for any J, and this has to be at most K. Okay, so that's very natural. The second set is actually much less clear, so let's focus on this. So what does the second set of constraints say? It says that for every day I, and for every subset of client S, if I look at this strange sum, so the sum of Pij, Xij, it's at most half the total processing time in S squared. So, actually, I mean the total processing time of the jobs of S on day I, okay, of the clients in S on day I, and 2 here means that we take it squared. Okay, so you look at any subset S, and you look at any day I, and this strange sum has to be half the total processing time of the set squared. The total processing time of the set on day I. Okay, why is this? So the point is that this constraint holds for any solution, not necessarily K fair or whatever. This set of constraints should hold always for any solution. Why? So first, if you think of a singleton set, suppose S contains a single job, then this strange sum is just Pij times Cij. Cij is at most Pij, right? It's at most the completion time of a client's job is at most its processing time. So this is at most Pij times Pij, which is more than a half Pij squared, and Pij squared is exactly Pis squared. So it's easy to see that the constraint is satisfied for a singleton set. If you take a larger set and you look at the sum, what happens here is for any 2 jobs, let's say J and K S, you would have either Pij times Pik or the reverse of this. So you will always have the term Pij times Pik. Why? One of them is scheduled before the other. And if you look and if you think about the completion time includes the processing time of all jobs, including client J's, and all jobs that precede client J's job. Therefore, if K precedes it, we have Pij times Pik, and we have the reverse in the other case. And in any case, this sum is greater than summing up over all pairs J smaller than K, Pij times Pik. Now, this is exactly half of this term here. So taking Pij, the sums of Pij's in S squared, the sum of it, and taking it squared, and then O plus half of Pij squared, sum, which is greater than this term here, which is exactly half of the total processing time in S squared. Okay, so this constraint in general is satisfied, should be satisfied by any schedule just because of how the completion time objective behaves. Therefore, any K-fair schedule is a feasible solution to our LP. Now, you can notice that there's an exponential number of constraints in our LP because of the second type, right? There's a constraint here for every subset of jobs. But luckily, this LP has what is known as a separation oracle. This is due to Poirel from Math of Programming Net 3. So what is a separation oracle? It's simply an algorithm which receives a solution and in polynomial time determines whether the solution is feasible. And if it's not feasible, it returns a constraint that is violated by the solution. Okay, so in polynomial time. So it's like a black box, you give it a solution, it returns either says this is fine or returns a violated constraint. And if you have such an algorithm which runs in polynomial time, it's well known that you can use the prime and dual method in conjunction with this oracle to solve LPs with an exponential number of constraints, even with an exponential number of constraints in polynomial time. But again, the polynomial is pretty terrible. Okay, but still we can solve this NP in polynomial time, a big polynomial, but we can solve it. And we obtain optimal solution x11 star to x star and m for the LP. And we use this optimal solution to construct a schedule for our problem, for the jobs. So we cannot just simply round these variables, these fractional completion times, because they can be fractional, and once we round them, we could get something infeasible, or not even something that doesn't even make sense. So instead, what we do is we do the following. For each day I, we construct a schedule as follows. We simply sort the clients in increasing order of xij's. So I is fixed and j is not, and we sort the clients in this order. And this is the schedule we produce for day I. Okay. So in this case, the the total completion time of client J is simply on day I is simply the sum of processing time of all clients that precede him on this day, including himself. And now we claim that our solution is too approximate. Why is this the case? So fix any day I and fix any job client J and consider the job of client J on day I. And now let's and consider day I and look at this optimal schedule. Look at our schedule on day I. And let SL denote the subset of clients which precede on our schedule client J on day I, okay, including J itself. So by our construction, we know for this set SL, the total completion time of Cij is exactly Pi of SL, the total processing time of all jobs in SL on day I, of all clients in SL on day I. So Cij equals Pi of SL. On the other hand, since the optimal solution is feasible, and we know by our construction that xij star is the largest value x of x star in SL, we know that since the optimal solution is feasible, we know that this inequality holds because the optimal solution satisfies the second set of constraints for SL, or the constraint of type 2 for SL and AI. This equality holds, we know, because xij is the largest, x star ij is the largest x star value in SL by our construction, since j is the last job in SL on the AI. So we can take x star ij out of the sum and multiply it by the sum of processing time. And this is exactly PISL. So if we divide by PISL, basically what we have is that the completion time of client J on day I is at most twice xij star, right? The optimal fractional completion time of client J on day I. And from this, you immediately get that the solution is to approximate. You can look at any client. The sum of its completion time is at most twice the sum of xij star. And this is at most k star because xij star is a feasible solution. So the total completion time of any client is at most 2K star, which is exactly what two approximate solution is. Yes, and that's it. So this is how you obtain a two approximate solution. The algorithm is not so complicated, but behind it runs heavy machinery that runs in a lot of time. It would be very interesting if we can improve it. Okay, so moving on, let me briefly, very briefly before we conclude, sketch some further results. A much more sophisticated algorithm gives us the following theorem. We can show that the problem admits p-task if there's a constant number of days. And it involves a sophisticated batching scheme where we group jobs together and consider all of them completed at the same time. And this somehow helps us to construct a p-task. And we also consider the case where all days are the same. So where the processing time of every client is the same on any day. This is actually a very interesting and slightly weird problem. It's not even clear that it's an NP. If M is not given in unary, it's not clear that it's an NP because you could need a polynomial number, or you could need something like a fraction of n different schedules. And if n is given, and the actual input size is n times the processing time, maximum processing time, plus log n. So it's not even clear that the problem is an NP, but regardless of these weird situations, we can show that the problem admits a very simple algorithm that beats the two approximation algorithm that achieves this approximation ratio, and it runs in almost linear time. And we can also show that the problem in general, without a restriction on the number of days, admits a quasi-polynomial time approximation scheme. So an algorithm running in n to the log epsilon. Yes. So I still have 8 more minutes, or should I conclude?
Yeah, so if you can conclude, the time is
Yes.
up, right?
Perfect. So there are also, I'll just put the slide here for a second. We also studied the sigma uj objective. There are a few results on that problem as well. The just-in-time objective, which I just wanted to list some results that we obtained there. I won't have time to go over this, but all of the work we've done on fairness and repetitive scheduling appears in these 4 papers. 3 have already published. This is a work in progress. And the results that I presented in this talk are taken from item number 2 and item number 4. Thank you very much. Right, I even have a slide. Thank you very much for everybody's time and attendance and attention.
Okay, thank you. Thank you for your talk. And now let me ask if anybody is interested to ask the question. If not, then I can start. So I'm not really sure if I understood the repetitive or to which extent there is also release date, because you say that job, for example, I is on day J, for example, and it means that the job cannot start earlier, but it can finish later than on day J because it can be late, or how is it? So is the release date present in the problem or not?
In everything that I discussed, not. You could think of a release time during a day. So think of you could even generalize this more, but in my problem, in what I discussed, is there just a job every day.
Job.
So you can think of it as you get M different instances of a classical scheduling problem.
Oh, I see. So there is the client is coming every day. So the periodicity of all jobs or clients is the same. All of them are like willing to access the resource every day, right?
In the simplest case, yes. In what
Okay,
I
okay.
you can generalize
So
also using our model.
okay, so and if I need to add release date within the day, then the problem is completely different, I assume. So you have no assumptions how it will get complicated or
Exactly. It would make it harder. This is clear, but much harder probably. But we haven't looked into this.
I see. Okay.
We never considered release. This is wide open, and it's even more realistic.
I see. But anyway, the repetition is the same for all jobs, and this is one day. Okay. Mhm.
Yes, exactly.
Okay, so any other question? Nobody is asking, so I thank you once more. And the talk is recorded on YouTube if anybody wants to come back to it. And let me just mention that the next talk will be on October 15th, and it will be given by Shenghun Kwon from KAIST and Omelette Incorporated. And he will speak about learning-based approaches to combinatorial optimization in transportation. Okay, so thank you very much for being with us, and I'm looking forward to see you in 2 weeks. Thank you. Bye-bye.
Sorry, I do have a question. I was just a bit slow.
Yes.
Okay, just please go ahead, ask the question. Okay.
Thank you. So in the model you propose, you assume that you have all the M instances, all the M individual scheduling instances given. But
Yes.
I would guess in practice, it's more common that you know the history of, I don't know how many instances, and you need to decide online how to schedule without being able to wait with your decision until the next instances come in. How does this change the problem?
So I want to say first, you're right. This also happens, but also there are many cases where you know in advance the orders of the clients in the year. And especially if you think of medical, and less pleasant things, these are the periodic testing and stuff is much more predictable. Yes, but in the first you can consider this problem in the online setting where the days arrive online. And the second thing is probably to do what you suggested in your question is to actually construct from the history of your company or whatever, your organization, plausible predictions for the future. But before, if the online setting would be the more natural, and to understand the online setting, of course, the first thing to do is always understand the offline setting and then try to apply some ideas there to the online.
Okay, thank you.
Yeah, thank you.
Thank you very much. Any other question? If not, so let me conclude the session and looking forward to meet you in 2 weeks from now. Okay, thank you very much. Bye-bye.
Thank you, everybody. Bye-bye.
Thank you, Danny.
Thank you.